Yeah. So, hi, welcome to my presentation this afternoon at this lovely location at Red Hat. Thank you very much for taking care of us. Really appreciate it. I'm Stefan, and today I'm going to tell you something about software sustainability in the context of flows. I'm Stefan, and I work as a security researcher at Fraunhofer AISEC based in Garching, nearby Munich. And I work in the department Product Protection and Industrial Security. And what we do is we act as some kind of gateway between the hardware guys and the pure software guys and the cloud guys. And my area of studies in particular is software testing and software pen testing, especially in the automotive domain. I do code reviews and I work on certain aspects in software supply chain topics. As we're in the public sector, we're partially publicly funded. 1/3 is industry work and 2/3 roundabout is research work. And as a consequence, we collaborate with a lot of OEMs and tier 1 suppliers. Since this talk is basically about my PhD thesis, you can find the thesis at this very location. How can you motivate this work? It all dates back to 2015, where the 17 so-called Sustainable Development Goals by the United Nations were defined. And the term sustainability is at the very center of these goals. The University of Limerick, where I did my PhD on, has its own agenda how to fulfill these goals. And they have a mission statement document where it is written that each graduate will take the ability to contribute to a more sustainable world. In other words, I'm the expert now on this topic, and I can tell you something about that. It dates back to a publication from 2011, where the term software architecture sustainability was defined. And it was defined as the ability to endure by evolving, which means, let's imagine you have a piece of software, and the target is to make that piece of software to stay valid as long as possible by avoiding repetitive errors, maximize synergies between products, strengthen collaboration, develop robust interfaces, and last but not least, avoid fatal design decisions concerning the architecture of a software system. One example for problematic decisions might be the transition from Python 2 to Python 3, which took the community over 10 years to fully complete that transition. And the key challenge in this topic is universally solved problems at a lower layer. What does the industry? We all know the Rust programming language, where the Rust for Linux project emerged the last years. And the basic idea is just move the memory safety problems, the solutions for the memory safety problems into the compiler, into the language level, and just don't think about it. What we use is Rust in its assembly line. We have Rust code in Android and its DNS stack, and even Microsoft considers Rust in its kernel code nowadays. I had a student last year who analyzed the Debian distribution of actually how much so-called memory safe code, as defined by the Federal Ministry of Cybersecurity in Germany, how much memory safe code is actually right now in the Debian distribution. And we came up with this little graph. We counted all lines of code in all Debian packages, and here with these bluish bars, you can see that Rust code, memory safe code in general, in the Debian releases kind of increasing. That's might be good, and we might indicate that critical CVs are steadily decreasing, but we need a lot of more research in this topic. We need a lot more data. However, this talk is not about Rust. It's about more general problems. You might know that little graph over there. It's from XKCD, which shows a fictional example of software dependencies. And it shows that particular risk marked by the little arrow over there, that developers start to use components in their applications in the form of software libraries or software modules. And the risk is that a serious bug might cause the shaky construction to collapse. A further risk is serious bugs might be introduced intentionally by malicious players, and we call that supply chain attacks. In the past, we had some very famous CVEs. You might know that one, Heartbleed. It's about 10 years ago. It might be solved by just using the Rust programming language. We also had shell shock, which was a conceptual mistake in the code that might be not addressed by just using Rust. It goes deeper. It goes into the conceptual part of the design. We had log4shell also. We had problems in AISEC, which was a path traversal. And we had the XC utils backdoor, which was basically maybe, especially from my point of view, the maintainer had too less funding and he was affected by a malicious player, and that's bad. And that thoughts lead me to the question, what are the current challenges in the FLOSS domain? I had a publication 2 years ago where I examined the Quick ecosystem. And Quick is a major recent development for the internet, especially because the most recent version of HTTP is based on Quick rather than TCP plus TLS and forms the backbone of the modern web. It includes a bunch of improvements. However, the ecosystem seems fragmented since everyone seems to run his own Quick stack, there's no reference implementation available and so on. And however, such protocols are defined by IETF in so-called RFC documents, and such documents contain so-called security consideration section, where conceptual weaknesses in such protocols are documented and measures against them are suggested. Unfortunately, these considerations usually are declared optional. And I came up with a research question, do complex and whether complex standard documents lead to insecure software ecosystems. In other words, whether they lead to insecure and incompatible implementations from a security perspective. And what I did was I looked at various different implementations of the protocol. Just to highlight a few of them, I looked at the one which is at QuickGo, which is used by the Caddy web server. I looked at the Cloudflare one, which is used in the Android DNS stack, Microsoft one, which is used in the Samba stack, and so on. The result of this research was basically this table. We have at the rows, we have the security considerations from the RFC document, and at the columns, we have the libraries that were examined. The first finding was that these guys were developed in private, which means there was no public discussion available. The documentation was a bit limited, and the developers just committed chunks of code on a regular basis into the Git repository. There was no public code review available and so on. And I would argue this is kind of bad for open source software. There are good examples as well. Every project has addressed amplification problems in its code. That's good. However, complex topics such as this one or this one were just addressed by single ones. We also found out that required features were not implemented for that one. And even there was a additional RFC that had the traffic analysis security consideration as a dependency, but was just not addressed at all. And we had a student who drove this work further. He created a test suite and will publish that as an academic paper in the near future. And he looked at, that's just an example of the results of his test suite for the slow loris problem. And we can see here check marks and the red crosses that, yeah, the situation is different, and that should not be the case. Every project should just address these issues properly, and that's not the case. Another ecosystem, let's say, is the X509 world, which is used for certificates. And Quick uses TLS for ensuring its security, which relies on this technology. Compared to Quick, this is based on a legacy standard which dates back into the 1980s. And in a subsequent study with a very similar idea, I examined parsers and looked whether their implementations have the same parsing results. That was the methodology of that research. I took as input, I took valid X509 certificates from census.io. That was a research data set, a few terabytes of size. I put the data into the parsers, GNU TLS, OpenSSL, Go, and a few others. And I recorded whether the output could be parsed or not. If it was a success, it was not interesting at all. And if it was an error, it was stored in the database. The result is that tested libraries do not agree with each other about which certificates are actually valid. OpenSSL has very little error rate, which means it just parses everything. And WolfSSL, on the other hand, does not agree with 13% of the tested certificates. Digging deeper revealed that some of these libraries perform additional checks at the X509 layer and others don't. OpenSSL just has this number of errors, and when you look at the column in this table, you see that the numbers are even different. And I would say that's bad. Using this dataset, furthermore, detailed investigations can be conducted. Implementations, for example, do not agree about invalid version numbers. They do not agree about invalid crypto parameters, and they even regress across different releases. In this particular case, the ASN1 parser was written by the project, and they regressed. We see that vaguely written specifications, the optional parts in the specifications to be more concrete, causes technically different implementations. And this thought leads to the question, how can important software components, in other words, dependency in the FLOSS ecosystem, be pinpointed? And why do we want to pinpoint these projects? Each dependency has a cost, and the overall cost increases with each added dependency. However, in order to reduce the number of available Bs in that equation is taken from Russ Cox. He had an article that was the former Golang project lead. He came up with that equation about dependencies. And in order to reduce the number of available Bs in that equation, as a first step, relevant projects have to be identified. And what I'm talking about is projects marked by that arrow. There are approaches in academia based on so-called graph theory. The buzzword here is centrality. I won't go into details. We can discuss that later. For specific ecosystems, research does exist. However, most of the time, system dependencies are overlooked. In other words, there are, for example, studies available that examine the Python packaging index. And what is overlooked is the Python packaging index does not take care of system dependencies in that case. Yeah, and that's a problem. I call it cross-ecosystem dependencies are not always tracked correctly, and that might cause inconsistencies in our tooling, and that's a point we need to address. I tried that approach in the Nix OS distribution, and I created a dependency graph of all the packages, and I applied the centrality, and I ordered all these packages, and that was the result. Amongst that 13 top libraries, in other words, the most important libraries, that one is OpenSSL, Bash, XC, and I showed you the CVs in that one of my first slides. That approach is able to highlight and pinpoint packages with a large impact by just apply a clever ordering to graph nodes depending on their centrality value. However, as a next step, assessing the software health, especially for non-GitHub repos, is current research topic, in my opinion. I have a mentionable effort on this topic. A friend of mine presented this year at Foster, and he drove that topic further at the ALPS conference in Innsbruck this year. And he developed a method to trace the build process of Debian packages using an own Fuse file system driver. And he created a build graph. And with this approach, he was able to detect the XC vector during the build process. And let's try to make a summary. What are the conclusions? What are the current challenges? On the one hand, we have vaguely written specifications. We have the one that I showed you earlier. And we need to find important projects and bring them into good shape in order to avoid situations like the XC vector in the near future. In order to pinpoint issues in software ecosystems, there are available algorithms that we can just use. However, there are no standardized maintenance and vulnerability tracking available, especially for non-GitHub repositories. SBOMs, in this case, help, but from my point of view, we need them as a first-class citizens in our packaging tooling.
And do we need them effectively, not just at the component level, but down to the source level or not?
Yeah. That's up for discussion, I would say. There are many different use cases, I would argue.
Sources, that's my bias.
Yeah. My opinion is based on this master thesis I came up with. The author presented this weekend.
Yeah, he was at B-sides.
Yeah, I was subscribed to that workshop, but I couldn't make it, unfortunately. But he shows that the available tooling just shows inconsistencies in the SBOMs that you get. And that's, from my point of view, one thing.
The available tooling is not pulling into the system level, to your point earlier.
Yeah. And my last point, yeah, we can estimate the sustainability of software by metrics such as password to license, number of reverse dependencies. However, that needs further research. I found a paper the authors created a machine learning model for assessing the health status of a software project. However, it was GitHub projects only, and the authors didn't publish their machine learning model. They just published their results, and the server is offline. Wow, that's unfortunate for
Okay, so
but that was a very
startup.
yeah, maybe that's one thing we would need in order to find that project marked by the error. Let's come to the research conclusions. In order to improve our software architecture sustainability, we need to improve standardization processes in terms of being simple and unambiguous to implement. We will need to find and address insufficiently maintained projects, not only track them, but also support them. We need to better pool our resources. I found that there's a lot of duplicate work, and we just need to combine it and just move on. And we need an overarching solution. We need to simplify stuff. And last but not least, we need to teach the industry partners that they should use the available tooling. In other words, for example, they should just use a package manager and not just copy paste C libraries into a project and completely forget about it. I have seen this a lot during my industry work, and that's very bad. In the end, I want to just credit my excellent students who helped me with this work. If you want to hire them, just contact them. And thank you very much to the Alpaca Research Project, and thank you very much for your attention. Any questions?
Second. So we're about to have so yeah, you've got about 5 minutes for questions. Anyone have any questions?
Questions?
Yeah. So you had two very nice examples of where specifications were not precise enough. Do you also have counterexamples where they are good and good enough to having worked with the ADA programming language? And this one has like probably the most comprehensive specification that I've seen. But on the other hand, leads to a situation where the specifications just predict to be practical. So I guess it's difficult to find a good medium ground.
I have not a good example, but I have a different example. I came up with an approach in order to formulate RFC documents in machine readable language. There is a paper. I have not the reference here by hand, but I can find it. And this language has the feature that you can generate actually code from it, and humans can read it as a specification. And that was kind of an interesting idea because you have the implementation and the specification at one location. And the problem with RFC documents, from my point of view, is that you have these large documents written in prose with should, must not, and so on. And you need to transfer that into code by hand, and that's kind of error prone. Oh, I kind of addressed the question.
Yeah, kind of, yeah.
Related to it, there was the safe systems part. Last year at Plumbers, we also had some guy who was going through like OpenVG, OpenCL, some kind of framework, I don't remember exactly, who was also pointing out to the specification and how the formal specification would have or would help to create better generatable code and giving also more details on where the language used by humans, which are often not non-native speaker, or which could be impacting the specification. So if there's an interest on this, just you can check most likely on the last year's Safe Systems with Linux Plumbers recording on, I think it was open.
Yeah, no.
But it was open, OpenCV, OpenVG, open. I need to double check. At least there was a good. It's just one of these formal specification side. You also encountered a lot of issues with the standard specification.
Yeah, it's a very complicated topic. Yeah, you had a question.
Yeah, you have shown metrics with quick stacks versus their problems. And how did you find the problems? Have you done code review for that or used a standardized conformance testing suite?
Yeah, I forgot to mention that in my presentation. In my paper, which was the first one on this direction, I chose a manual approach. I looked at the source code in order to find whether these security considerations are addressed. You might know you have a lot of code to look through and you might use it. Then I looked at documentation I found, bug trackers, pull requests, mailing lists, and so on. And I tried to get my head around this in order to make a cross or a check mark in the table. However, we had two students. It was Arne and Katzper, and now we have a comprehensive test suite which actually tests these security considerations. We created test cases, and you can just throw a quick library into it, and you can just say it's implemented or not. Yeah.
But it's specifically for quick implementations, not more general health metrics for.
No, it's for a quick, and it is especially for the security considerations which are documented in the quick RFC, in RFC 9000 to be particular. Yeah, and that test suite, we intend to publish that as an academic paper. Yep.
Just one remark on your two statements, namely Python 2 taking about 10 years to be deprecated and code being randomly copied and forgotten about in the industry. So I strongly disagree with the 10 years. Because I know a shitload of projects still hacking shit in Python 2. So
okay.
No. And
thank you very much for that.
No, it's just crap. I mean, now we're getting a bit out of your specification turf and into mine, which is basically building systems.
Yeah.
And one of the biggest problems that we see is building systems is not fun. So people just beat at it long enough until it does one time what they want, and then they just continue shipping it.
Yeah.
Python 2 is a perfect example. Copying code into industry project is a classic example. Shipping outdated Yocto versions is a classic example. And Ubuntu just announcing 15 years of LTS support is exactly the same example because somebody beat Ubuntu 14.4 long enough until it did what they wanted, and so they keep on shipping it.
Yeah.
I mean, we can write specifications and tests and everything as much as we want, as long as people ignore the technical depth that they are trying to hide.
Yeah.
We're in shit real deep. And yeah, I'm the offensive German. I use that language. Sorry.
That's okay. Yeah. Thank you very much for your comments. I'm not sure if I can add anything to it. Just one idea about the topic of copy pasting code and the long support times. It transfers into a problem when the responsible people change and nobody knows what is in that package. And then it comes to the security guys like me and they, say, what are you doing actually? That's a problem. And from my point of view, in my wish list, we need to stop this somehow.
Okay, how about the AI generated code?
I did not look at AI generated code. That was out of scope.
Okay, I think we're pretty much at time right now, so thank you very much.
Thank you very much.
We'll resume in 15 minutes. Please grab fresh coffee if we better.
Philip, can you stop the recording?